In this video, we're going to solve applied problems involving ellipses. Ellipses are found in many applications in science and engineering. For example, the orbits of the planets around the Sun are elliptical, with the Sun's position at one of the foci. This was first discovered by Johannes Kepler in the 17th century as he was studying the orbit of Mars. The image we have on the slide is of Earth orbiting around the Sun, where the Sun is at one focus of the elliptical path. On this slide, we have an image of the Whispering Gallery in the Museum of Science and Industry in Chicago. The room is designed with an elliptical ceiling. Ellipses have an interesting reflective property. A person standing at one focus of the ellipse can whisper and be heard by a person standing at the other focus, because all of the sound waves that reach the ceiling are reflected to the other person. And this is true for any wave such as a light or sound wave. This principle is also used with sound waves in water to amplify the effect of the waves and fragment a patient's kidney stones without the need of surgery. In this example, we're going to learn about planetary orbits. And before we solve a particular problem, let's first learn about some terminology. In the given image, we have the graph of an ellipse representing the orbital path of a planet around the Sun. The Sun is placed at one of the foci. We also have the major axis drawn and the center of the ellipse labeled. Three terms are going to be defined here. They are the aphelion, spelled A-P-H-E-L-I-O-N, perihelion, P-E-R-I-H-E-L-I-O-N, and mean distance. The aphelion of a planet is its greatest distance from the Sun, which is the distance from one focus to the furthest vertex along the major axis. The perihelion is the planet's shortest distance to the Sun along the major axis. That is when the planet is at the other vertex closest to the focal location of the Sun. The mean distance of a planet from the Sun is the length of the semi-major axis of the elliptical orbit. In other words, it is the length of half of the major axis, the distance from center to a vertex. Now that we have defined the three terms, let's solve an example. And the problem states, the mean distance of Mars from the Sun is 142 million miles. If the perihelion of Mars is 128.5 million miles, what is the aphelion? Find an equation for the orbit of Mars about the Sun. So first, let's begin by sketching an XY coordinate plane. And let's place the center of the ellipse at the origin. Let's then sketch a rough picture of an ellipse so that the major axis lies on the x-axis. So this means the equation of the ellipse will have the form x squared divided by a squared plus y squared divided by b squared equals 1. Now recall that the vertices are a distance of a from the center, so let's plot and label on our graph both vertices at the points -a, 0 and a, 0. Also, we know the endpoints of the minor axis will lie on the positive y-axis at the points 0, -b and 0, b. Finally, we can plot and label the foci of the graph, but let's only concern ourselves with the location of the Sun, which we will place a distance of c to the right of the center at the point c, 0. So now let's find the aphelion as requested in the problem. We are told that the mean distance is 142 million miles, and this is the distance from the center to a vertex. Therefore, we can write that as an equation of a is equal to 142. Now, I'm going to leave the unit of millions off of each of these numbers, and in this case, just write a equals 142, but we know the magnitude of these numbers are in millions of miles. Now, we're also told that the perihelion is 128.5 million, so I will write this down as PE equals 128.5. Now this isn't necessarily a standard notation, but I'm using the letters PE to denote this distance. And we are being asked to find the aphelion. Now I will denote this symbolically as AP equals question mark, just reminding ourselves we are looking for that distance of the aphelion. All right, now the sum of the aphelion and perihelion is the length of the major axis. And we can write this as an equation as PE plus AP is equal to 2A. And we know the value of PE and the value of A, so this equation becomes 128.5 plus AP equals 284. So now subtracting 128.5 from both sides, we calculate the length of the aphelion as AP equals 155.5 million miles. So this answers the first question asked in the problem statement to find the aphelion of the planet Mars. And we are also told to find an equation for the orbit of Mars about the Sun. Now in the beginning, we wrote the equation as x squared divided by a squared plus y squared divided by b squared equals 1. And we know the value of a, and thus a squared, and we need to calculate the value of b squared. So to do this, we'll use the relationship that b squared is equal to a squared minus c squared. Now this necessitates that we calculate the distance c, which is the distance from the center of the ellipse to the Sun. From our diagram of the orbit, we can note that the value of a minus the perihelion will be the distance c. So we can write c is equal to a minus pe, which equals 142 minus 128.5, which is 13.5. Again, recall this is a magnitude of millions of miles. Now that we have the value of c, let's come back and calculate b squared being a squared minus c squared, which equals 142 squared minus 13.5 squared, which equals 19,981.75 millions of miles. Now, since we have the value of b squared, we can write the equation of the elliptical orbit of Mars as x squared divided by 142 squared plus y squared divided by 19,981.75 equals 1. Let's put a box around this equation to show that we have answered the second question in the problem statement to find the equation of the elliptical orbit of Mars.